information criteria, Occam's razor, and inference to the best explanation. Conventional statistical decision-making often leans heavily on the concept of the p-value. While seemingly straightforward, this approach presents several fundamental problems. Primarily, a fixed and absolute significance level, typically 0.05, is applied universally, regardless of the context. This black and white perspective oversimplifies the nuanced reality of evidence, where effects exist on a spectrum and uncertainty is inherent. Additionally, decisions based on p-values often stem from a single statistical analysis, potentially overlooking alternative models that might better explain the observed data. This narrow focus can lead to premature conclusions and a limited understanding of the underlying phenomena. In contrast, relative model selection criteria, like the AICc information criterion, AIC, its corrected version, AICc, and the Bayesian information criterion, BIC, offer a more robust and insightful approach by focusing on model comparison. For example, when deciding whether to include a quadratic term in a regression model, researchers can fit both the linear and quadratic models and compare their information criteria values. The model with the lower value is preferred as it balances the trade-off between goodness of fit and model complexity, aiming to minimize expected prediction error, rather than judging a single model in isolation against a null hypothesis. These criteria evaluate a set of candidate models against each other. By considering multiple plausible explanations for the data, we gain a more comprehensive understanding and avoid the pitfalls of relying solely on a single analysis. Imagine you're shopping for a camera. Would you walk into Best Buy and immediately buy the first one the salesperson recommends? Probably not. More likely, you'd compare different models, contrast their features, weigh the pros and cons, maybe even check prices on Amazon, eBay, and elsewhere. In that sense, model comparison isn't some abstract statistical procedure. It's just a formal version of the kind of everyday judgment we make all the time. The original AIC, developed by Hirotsugu Akaike in 1973, takes the number of parameters and the likelihood function of the estimated parameters into account for measuring model complexity. AIC is better than R-squared and adjusted R-squared, which always go up as additional variables enter in the model. Put bluntly, the R-square approach favors complexity. In contrast, AIC does not necessarily change by adding variables. Rather, it varies based upon the composition of the predictors, and thus it is a better indicator of the model quality. AIC corrected is a further step beyond AIC in the sense that the former puts the sample size into the equation and imposes a greater penalty for additional parameters. Bayesian information criterion, BIC, is derived as an approximation to a Bayes factor, which compares the posterior probabilities of models under a Bayesian framework. Both BIC and AIC share the same basic logic. Better fit is good, but simplicity is better. However, BIC's penalty against complexity is heavier than that of AIC. The application of AIC, AICc, and BIC spans both traditional statistical analysis and the burgeoning field of data science. In traditional statistics, when researchers are fitting regression models, time series analyses, or structural equation models, these criteria help in selecting the most appropriate model from a set of plausible alternatives. In data science, where the focus often lies on building predictive models, AIC, AICc, and BEC are invaluable for tasks like feature selection in machine learning algorithms or determining the optimal number of components in clustering techniques. For instance, when building a time series forecasting model, different autoregressive and moving average orders can be compared using the Bayesian information criterion to select the model that best captures the underlying patterns without being overly complex. The theoretical foundation of AIC corrected, and BIC lies in the realm of information theory. At its heart, information theory, pioneered by Claude Shannon, deals with the quantification of information. One key concept is entropy, which measures the uncertainty or randomness in a system. When we fit a statistical model to data, we are essentially trying to capture the information contained within that data. An ideal model would capture all the relevant information and none of the noise. However, in reality, any model will lose some information about the true underlying process. The Kullback-Leibler (KL) divergence is a measure of this information loss between the true data-generating process and the approximating model. While the true KL divergence is unknown, AIC provides an estimate of the relative KL divergence between different candidate models. Similarly, BIC can be derived from a Bayesian perspective, approximating the Bayes factor, which represents the evidence for one model over another. By model comparison, the model with the lower information criterion value is estimated to have lost less information. Therefore, among the candidate models, it's considered to be a better approximation of the truth and is preferred. Although the information criterion does not directly measure information gain, the selection process inherently favors models that minimize the estimated information loss, which can be seen as maximizing the retained or gained information relative to other models. The information criteria, in their preference for simpler models that adequately explain the data, are akin to the philosophical principle of Occam's razor. Occam's razor, attributed to the 14th century English Franciscan friar and philosopher William of Occam, is often summarized as entities should not be multiplied beyond necessity, or, more simply, the simplest explanation is usually the best. Consider this metaphor. If two cars have the same horsepower and performance, I would choose the one that is easier to drive, such as fewer buttons on the control panel. After all, why wrestle with complexity when a smoother ride gets you to the same destination? It posits that when faced with competing hypotheses that equally explain the observed data, the one with the fewest assumptions or parameters is generally preferred. The information criteria formalize this intuitive idea within a statistical framework. By penalizing models with more parameters, they explicitly favor models that achieve a good fit to the data with less complexity. In other words, you can gain more by trimming redundancy. The principle of gaining more by reducing complexity aligns with the famous phrase, "less is more," often attributed to Ludwig Mies van der Rohe, a pioneering modernist architect. He championed this idea as a design ethos, emphasizing simplicity, clarity, and minimalism, core to the Bauhaus and modernist movements. Likewise, information criteria like AIC and BIC reward models that achieve explanatory power with fewer assumptions, embodying the same minimalist ideal in statistical form. While AIC, AICc, and BIC all serve the purpose of model comparison, they differ in their penalties for model complexity and their asymptotic properties, like behavior with large data sets. AIC tends to favor more complex models, as its penalty for adding parameters is relatively smaller. This makes it potentially more prone to overfitting, especially with limited data. AICc addresses this issue by introducing a correction term that increases the penalty for complexity with smaller sample sizes, making it a better choice when the number of data points is not substantially larger than the number of parameters. BIC, on the other hand, imposes a larger penalty for model complexity compared to AIC and AICc. As the sample size grows very large, BIC tends to consistently select the true model, assuming the true model is among the candidates. However, with smaller datasets, it might over-penalize complexity and favor simpler models that underfit the data. Taking all of the above into consideration, the choice between AIC, AICc, and BIC depends on the specific situation. AICc is often recommended when the sample size is small relative to the number of parameters. For larger datasets, BIC might be preferred if the goal is to identify the true underlying model, while AIC can be a good choice when the focus is on prediction and a slightly more complex model might capture subtle patterns. No single criterion dominates. In machine learning pipelines, it is common to minimize AIC first and use the Bayesian information criterion as a reality check against overfitting. These information criteria can be seen as statistical implementations of a broader philosophical idea known as inference to the best explanation, IBE. First formally articulated by philosopher Peter Lipton, IBE is the reasoning strategy where we infer that the best available explanation of the evidence is likely to be true. In the context of model selection, AIC and BIC embody this logic. Given a set of candidate models, they aim to identify the one that provides the best trade-off between goodness of fit and complexity. However, this alignment with IBE brings with it a key philosophical vulnerability: the bad lot problem. Lipton himself acknowledged this critique, which originates from the idea that if all the available explanations are flawed, then inferring the so-called best among them does not necessarily bring us closer to the truth. In statistical terms, if every candidate model in our set is misspecified, perhaps because they omit important variables, assume the wrong functional form, or rely on unrealistic distributional assumptions, then selecting the best among them using AIC or BIC is like choosing the least wrong answer from a menu of incorrect ones. It's like being on a reality dating show where your final three choices are a conspiracy theorist, someone who ghosted you last week, and your ex. You're forced to pick the best, but love isn't exactly in the air. In conclusion, while p-value-based decision-making offers a seemingly straightforward approach, its inherent limitations in being a one-size-fits-all, absolute measure based on a single analysis can be problematic. Relative model selection criteria like AIC, AICc, and BIC provide a more nuanced and robust framework by comparing multiple plausible models, grounded in information theory, aligned with Occam's razor, and being compatible with IBE. These criteria estimate the relative information loss, or, from a Bayesian perspective, the evidence for different models. Their application spans traditional statistical modeling and modern data science, aiding in tasks ranging from regression analysis to feature selection. What do you think? Have you used AIC, AICc, or BIC in your own projects? Please drop a comment. I'd love to hear how these criteria shape real-world decisions in your field. If you found this video informative, please share, like, and subscribe. Mahalo.